My name is Rebecca Monge, and I looked at Arctic climate change using novel visualization techniques that can aid in understanding climate change as a whole. Specifically, I looked at polar amplification, which is the accelerated rate of warming in Arctic areas compared to the overall Earth. Polar amplification is already documented to be up to 4.5 times faster than Earth's global warming rate. Researchers have determined that Arctic feedback loops, such as the ice albedo or atmospheric heat transport feedback loops, play a large role in this. However, there's uncertainty regarding just how the mechanisms of these causes work. This is largely due to model biases, because climate models, which are used to study polar amplification, contain framework differences that produces a variation in results. Thus, I wanted to study polar amplification in a way that not only identified the mechanisms about it, but also eliminated as much model bias as possible, which can be done by studying multiple climate models as opposed to one. Thus, in order to do this, I used the CMIP initiative, or the Coupled Model Intercomparison Project. With it, I used the 6th version, or the most recent version, because the CMIP 6 version centralizes the data from multiple climate models from around the Earth, so I used 18 as opposed to just one. First, in the 18 climate models I used, I calculated polar amplification, and I found that on average, polar amplification in these models was about 2 to 3 times as fast as the overall Earth's warming rate. I then compared polar amplification and time period, specifically a near-term time period from 2020 to 2040 and a far-term time period from 2080 to 2100. I then looked at polar amplification and emission scenario. Emission scenarios are settings applied to models that allow models to predict futures of various ranges. A low emission scenario would predict a future where we've taken climate action, but a high emission scenario would predict a future where we have not. I used a low, a mid, and a high emission scenario in order to produce a various range of futures to compare with polar amplification. In this analysis, I found that polar amplification was not correlated to time period or to emission scenario, but this analysis helped me determine that in order for a variable to affect polar amplification, it needs to focus on Arctic regions. So I focused my analysis on Arctic regions for the next part, which involved plotting zonal means, which are snapshots of Arctic regions, to find a geographic and spatial representation of trends in polar amplification. Specifically, I did this by using Python 3-based programming packages such as Xarray and platforms such as JupyterLab. These computational technologies are not traditionally used in climate change research, but I wanted to use them because they're great for result reproducibility and data provenance tracking. By using Xarray and JupyterLab, I plotted zonal means of the Arctic for 5 variables correlated to Arctic feedback loops: temperature, snow cover, cloud cover, and latent heat flux and sensible heat flux. The zonal means are showed here, and I was able to identify patterns from the spatial representation. As you can see in the temperature zonal means, polar amplification increases left to right. And in the lighter area here, from 0 to 50 degrees east longitude, which is the Norway and Arctic Sea area, this area increases as well. Because it increases in size as polar amplification increases in value, there's a direct correlation between the Norway area temperature response and polar amplification. This direct correlation is also seen in the latent heat flux zonal means and in the sensible heat flux zonal means, which are not pictured. Finally, I looked at snow cover and plotted zonal means for this area as well. Here you can see that the area from 250 to 350 degrees east in longitude decreases in size. This area is Upper Greenland, and since it's indirectly correlated to polar amplification, such spatial representations reveals insight to this geographic area as well. Overall, using Python 3 packages such as Xarray and JupyterLab, although non-traditional, provides an avenue of analysis that has not been done. This visualization allows for the determination of trends, specifically geographic factors that play a role in polar amplification. As seen here, the Norway factor in temperature and heat flux response may be directly correlated, and the Upper Greenland area may be indirectly correlated in terms of snow cover response. This suggests that there are regional drivers to polar amplification, which not only can shape climate policy, but it can also provide an avenue of analysis for other climate change phenomena. All in all, this study demonstrates a new technique that may not only contribute knowledge towards polar amplification, but towards the mitigation of climate change as a whole.